Now, the back page will actually involve a lot of the same type of thinking. Um, so what I want to point out though is a lot of times when you make these charts, we don't know what the graph will look like right away. So if we kind of look for patterns, for instance, like number 4, we know this is linear because linear functions always have a slope and a y-intercept. And so looking at this, you can kind of think of this as y equals mx plus b. So when we graph it, an equation that's set up like this is either going to have a positive slope, negative slope. It could be a vertical, or excuse me, it could be a horizontal line. If it's a function, however, it's not going to look like this. It's not going to be a vertical line. And the reason being, this would not pass the vertical line test. So every input would not have distinct outputs. All right, so we're going to plug in several different x values and use those outputs to create some ordered pairs on our graph, which after we get several points on there, we should get a pretty good idea of what this graph's going to look like. All right, so if I'm going to use -2 as my input, that just means, and my function, every time I see an x, we are going to replace it with -2. So up here I've just taken every x and I've replaced it with -2. So evaluating the right side only, we're going to get -10 plus 4, which is -6. So that means our input is -2. Our output is -6, and eventually we'll plot these ordered pairs on the graph. All right, let's try another one. An input of -1 means we're going to take -1 times 5, and then we're going to add 4. So that's -5 plus 4 is -1. So if our input is -1, our output is -1 with 0. 5 times 0 is 0, plus 4 is 4. So an input of 0 gives us an output of 4. With 1, 5 times 1 is 5, plus 4 is 9. So an input of 1 gives us an output of 9. And on the last one, an input of 2 means we're taking 5 times 2, which is 10, and adding 4, which is 14. So this will be 2, comma, 14. Input 2, output 14. Graphing this, we're going to have to probably scale a little bit to make it fit on the graph paper. So if we focus on the x's here, my x's go from -2 to +2. So I don't think we're going to have to scale our x-axis at all. And then our y's go from -6 to 14. So I'm going to try to put my x-axis a little above the bottom of the graph. That way I can get some of those negative outputs on my image here. So x-axis we can scale by ones. 1, 2, 3, and then going backwards, -1, -2, -3. And I think I said outputs, I'm sorry. Inputs scale by 1. Outputs, the y values, I'm going to scale by, let's see, 9's the largest, or no, 14's the largest, so looks like I could scale by 3's going vertically here. 3, 6, 9, 12, and 15. And then going down would be -3, -6, and I think that's as low as it goes. So my first ordered pair is -2. So back 2, down 6. Watch your scaling. Next point is -1, 1. So that's not one box. Since we scale by 3, it's about a third of a box. 0, 4 is going to be the y-intercept, which again makes sense because that would be our initial position. An input of 1 is an output of 9. An input of 2 is an output of 14. All right, and so if I connect the dots, oops, that's a little thick. All right, if we connect our dots, we got a line that looks, something like that. I'm just going to show you in GeoGebra what happens when we graph 5x plus 4. Just to help you see that this is a nice tool to generate a graph. I'm going to say f of x equals 5x plus 4. And I'm going to adjust my zoom a little bit here. All right, we can see a y-intercept of 4. And at 4, if our slope was 5, that means rise 5, run 1. Which, yeah, this all kind of matches up. If you go up 5, that'd put us at 9 over 1. The slope of 5 is shown here. And it matches our rough sketch that we created as well. So the points don't give you every point on the continuous function. It just helps you get a rough idea of what it will look like if you play connect the dots. All right. We haven't graphed any absolute values this year, but absolute values will always look like a V when you get done graphing. And so we're going to play the same game here. We're just going to insert different x values into the function, and then we're going to simplify and see what we come up with. So I just kind of chose some numbers here. You don't have to worry about choosing the numbers appropriately. We'll deal with that later in the year. But for now, I'm just going to insert each of these x values into the function. So on the first row, our input of 3 means we're going to replace x with 3. 3 minus 5 is negative 2. But realize when you take the absolute value of a negative 2, absolute value always makes it positive. So this will be positive 2 plus 6 is 8. So an input of 3 gives us an output of 8. All right. Go ahead and pause the video, and I want you to try the rest of this one on your own. Okay, now, as you were creating these ordered pairs, unlike linear, if you look at the trend here, linear functions kind of keep the same output pattern. In other words, like these outputs are getting larger. As you increase your x's, the y's also increase. Well, absolute value doesn't really follow that trend. Absolute value, as x's get bigger, for a while, the outputs or the y's were getting smaller, but then all of a sudden right here, they kind of turned around and got bigger. So that's what creates the V shape in your on your graph. So all of our outputs are positive. So I'm going to try to draw a nice straight line because that was bad. There we go. And our inputs I selected are all greater than 0. So I'm just going to put my y-axis over here, and if I count by ones, I think I can get enough inputs here to make it fit. 5, 6, 7. All right, and my outputs go all the way up to 8. 1, 2, 3, 4, 5, 6. So it looks like we have to count by twos. 2, 4, 6, and 8. Okay. So 3 comma 8 be about right here. 4 comma 7 about right there. 5 comma 6. 6 comma 7. And 7 comma 8. And there's that V pattern we talked about. So it should be fairly obvious when you get done that it does form a V. I'm always going to put arrows on the ends of these because we kind of randomly selected our X's. We could have chosen other X's and the graph would keep going. Kind of add that same idea up here. Since I selected the X's, we're going to just show that this is a nice continuous graph and it keeps going infinitely in both directions. All right, the last one. Erase all my writing there. Okay. F of negative 2. You got to be really careful on your exponents for quadratics. Okay. We are not going to square a 5 times. We're not squaring negative 10 here. We are squaring just the number that's in front of it. And so negative 2 squared is positive 4. Times 5 gives me 20. Take away 10 gives you positive 10. So don't square the product of these numbers. Just square the number that's next to it. All right, that's all the parentheses. The parentheses tell us that's what is applied to the exponent. All right, so that gives us 20 minus 10 is 10. So negative 2 gives us an output of positive 10. All right, try negative 1. So f of negative 1 is how you would read that. Means we're going to take negative 1 squared, which is positive 1, times 5, which is 5, take away 10, negative 5. All right, again, I'll let you try the next 3. You don't have to pause the video if you don't want, but as you're working, check these numbers. See if what my outputs are matching what your outputs are. Okay, after you've had a chance to try a few of these, just to talk through this last one, we put negative 2 in for our input. Negative 2 squared is, or excuse me, we put positive 2 in. 2 squared is 4, times 5 is 20, minus 10 is 10. So you're always squaring before you do your multiplying because you have to follow the order of PEMDAS. All right. The X's are counting by ones. Oops, crooked again. So I'm going to scale by ones on the x-axis. And then on the y's, we're going all the way from negative 10 to positive 10. So I think if we maybe scale by 5s here, we should be good to go. All right, so let's see what happens here. We're at negative 2 comma 10. So that's this point right here. Then we go negative 1, negative 5, so that goes down. 0, negative 10 is basically your y-intercept of negative 10. 1 comma negative 5. Notice we're starting to get a mirror image effect here. And positive 2, positive 10. So this is a quadratic graph. Quadratic is how we describe the relationship. and parabola is what is used to describe the basic shape of the graph. So that little smiley looking thing is a parabola. This equation, this relationship is called quadratic. All right, so we'll kind of use those words a lot second semester. Don't have to have those memorized, but we will deal with those a lot coming up. Okay, so in summary, how do we know these are functions? Well, we could definitely use the idea that every input generates only one output. Every x gives us only one y. Another thing to recognize is that the vertical line test, and I'll kind of demonstrate this, the vertical line test actually applies to every single one of these graphs. So if I draw a vertical line and I drag that vertical line across the graph, nowhere does the graph never crosses through that red line more than once at any given spot. So if I just randomly stop, like right there, the red line never crosses the graph more than once. All right, let's try it on the next one. From left to right, if I drag this across, the red line never touches the graph in more than one location. It actually doesn't even have to touch it at all. It just can't touch it twice. All right, even the parabola, even though as it gets steeper, it still is only going to cross through this line once because every input only has one associated output. So to kind of finish the sentence starter down here, we'll say they pass the vertical line test, meaning the graph never intersects a vertical line anywhere on the graph more than once. It never crosses through the graph more than once. All right, and that is essentially a visual way to check to see if what you have graphed is a function. One last thing here before we end this video, I want to graph this in GeoGebra just to kind of show you that what we are doing does work and it should match what you see in GeoGebra. So 5x squared minus 10 is our function. The name of the function is c, so I'm going to do c of x down here in the input bar is equal to 5x, and then squared has to be done with that little, it's called a caret key. All right, and I'm going to get rid of our other graph so we can see that better. All right, hopefully you kind of see these inputs and outputs. So we got input of 0, output of 10. Input -1, output is -5. Input of -2, output's 10. So yeah, this does actually perfectly reflect what we came up with on our graph without using GeoGebra.